Welcome back to the Math Professors. I'm Professor Van Hamlin, and today we're going to be solving differential equations using Laplace transforms. So if you like our free content, you want to help us grow our channel, please consider liking, subscribing, and sharing. So here's the method. We're going to be given an ordinary differential equation, and the way we're going to solve this is through Laplace transforms. So the first thing we're going to do is we're going to apply the Laplace transform. Now we're going to have this transformed differential equation, which is algebraic into capital F of S. We're going to solve this thing for capital F of S. So now we're going to have that solved equation. Then we're going to apply the Laplace inverse transformation, and it's going to return us the solution to that differential equation, which is really, really cool. Basically what a Laplace transform does is turn it algebraic, so all you have to do is just solve the equation. And then when you do the Laplace inverse, it immediately returns that solution. It's a fantastic little method here. Okay, so solve this differential equation. So this first order homogeneous differential equation. So I'm going to write it in this way as well, because depending on your book, they might use the primes. So I know in order to do this, I'm going to have to take the Laplace transform at both sides. So I'm going to Laplace this side, and I'm also going to Laplace this right-hand side. Now what we know is the Laplace, so the Laplace of this is going to be 2 times s capital F of s minus y naught, plus Laplace of y, which is going to be capital F of s. And this will be the Laplace of 0. Well, this will essentially be the integral of 0, which is going to give us 0. And then applying our initial condition, which is going to become a negative 3, so 2 times s capital F of s, minus that minus 3, which is going to be plus 3, plus capital F of s is equal to 0. And our job is to solve this thing for capital F of s. So I have 2s capital F of s plus 6 plus capital F of s is equal to 0. Solving for f of s, so I'm going to isolate that f of x after I send this 6 over. So we're going to have capital F of s, and this is going to give us 2s plus 1 is equal to that negative 6. So finally, capital F of s is going to be equal to minus 6 all over 2s plus 1. Now what we know we're going to have to do is do the Laplace inverse of both sides. So let's handle that. So Laplace inverse of our capital F of s is going to be equal to the Laplace inverse of this side as well. Now, this one's easy. This is just going to be y of t. Now over here, we have to do a little bit of work for this Laplace inverse, because it doesn't set up the way I want it. I want it to be the Laplace inverse of what I'm seeing is something like 1 over s minus a. And what I know is that's equal to e to the at, but it doesn't look exactly like that. So one thing I can do is I can pull out that 6, and also I'm going to pull out that 2, that negative 6 and the 2. So pulling out negative 6 over 2, we're going to have the Laplace inverse of 1 all over s plus a half. Now it looks like this. So y of t is going to be minus 6 halves, which is going to be equal to minus 3. And this is going to be e to the opposite of whatever that 1 half is. So this is going to be minus 1 half t. Or minus t over 2 if you prefer. Now it would be nice to kind of check to see if this is a solution, because that's kind of the claim that y of t is equal to this minus 3e to the minus t over 2 is our solution to this differential equation. So let's just do a quick check. If I want to check this, I'm also going to need to know dy dt or y prime. So y prime of t is going to be equal to, well, the derivative of an exponential is going to be itself multiplied by the derivative of what's inside, which is going to be minus 1 half. So this is going to be 3 halves e to the minus t over 2. So finally, plug it into the differential equation. I have 2y prime plus y is equal to 0. So 2 times y prime, which is 3 halves e to the minus t over 2, plus the original function, which was this original solution, which is going to be plus a negative 3e to the minus t over 2. And what we can see is, these will cancel, and these are opposite in sign. So this is true that both sides I get 0 back. So this is a solution. Now let's kind of walk through the method to make sure that we see what we did here. So first what we're doing is we're given an ordinary differential equation. So then we have to apply that Laplace transform. So once we have that, we have this transformed differential equation, which is algebraic in this capital F of S, which means I can solve this thing for F of S. Now, once I solve for F of S, I can now do the inverse Laplace transform, which is going to spit out my solution. All right, so let's do another example to finish this up. All right, so here's our last example. I want to solve a second order linear differential equation that is not homogeneous, so now it's equal to a function. And I just want to show you that using Laplace transforms, the method doesn't change even if it's second degree and also even if it's not homogeneous. So first we're going to apply the Laplace transform, solve it, apply the inverse Laplace transform, and we're going to be done. So let's do the Laplace of both sides. So y double prime minus 3y prime plus 2y, and this is going to be e to the minus 4t. Okay, so Laplace of y double prime is s squared capital F of s minus fy of 0 minus y prime of 0. Now minus 3 times the Laplace of this thing. Now y prime, so just kind of make sure that we remember how to find these derivatives, is that second degree means s squared. The next is going to be s, and then s to the 0, which is going to be gone. The first one's going to be capital F of s, and then you start with your function and then its derivative. So the s powers are going to decrease, and the derivative things are going to increase. So when I do this y prime, this is going to be s capital F of s. Now the s's are going to drop in power, so there's not going to be an s, and then we're going to start with our initial conditions and the derivatives. Plus 2 times capital F of s. And then the Laplace transform of that is going to be 1 over s plus 4. Now again, this is algebraic, and we need to go ahead and solve this for these initial conditions. So this is going to be equal to, we'll just evaluate at the initial conditions. This is going to be 5, and this is also going to be equal to 1. So we're going to get s squared capital F of s minus 5 minus 3s capital F of s minus 3 times minus 1 is plus 3 plus 2 times capital F of s is equal to 1 over s plus 4. And I'm just going to leave everything with the capital F of s over here. So s squared capital F of s minus 3s capital F of s plus 2 capital F of s. And then anything that doesn't have a capital F of s, I'm going to put to the other side. So I have this 1 over s plus 4. Now I'm adding s, and then minus 5 plus 3 is minus 2. So adding 2 to both sides. Now I'm not done solving. Isolating your capital F of s is going to leave this quadratic, s squared minus 3s plus 2, which I'm also going to have to put to the other side. So capital F of s is going to be equal to 1 over s plus 4 times s squared minus 3s plus 2 plus s plus 2 over that s squared minus 3s plus 2. Now we know that these things are, these quadratics are factorable. So I can rewrite this. This is 1 over s plus 4 times s minus 1 times s minus 2. Plus s plus 2 over s minus 1, s minus 2. So a lot of times I like to just combine these things. Sometimes it makes your life easier, sometimes it doesn't. It's kind of your choice depending on what differential equation you're working with. So I will do it this time. So in order to do that, I am missing this s plus 4. So I'm going to do s plus 4 to top and bottom of this side. So this is going to be an s squared plus 6s plus 8 plus 1. So what I'm going to have is capital F of s is going to be equal to s squared plus 6s plus 9 all over our denominators, or the factors in our denominators. Now if I was asking you to integrate something like this in Calculus 2, what you know is the method would be this partial fractions method. that there will be some a, b, and c that'll make this side of the equation equal to this side of the equation. And since these things are linear denominators, we have a really quick method like that cover-up method. So if I want to find a, well, a is going to be, what you do is you cover up this s plus 4, and then you plug whatever makes this thing 0 into this equation. So that's going to be negative 4. So I'm going to have a minus 4 squared plus 6 times minus 4 plus 9 all over, remember we're leaving the s plus 4 out, so we have minus 4 minus 1, and then minus 4 minus 2, and when we're done with this, 16 minus 25 plus 9, so we're going to have 1 over 30. Now we can do the same thing for b. So b it's going to be for this s minus 1. So I'm going to plug in 1 everywhere after I cover that up. So 1 squared plus 6 times 1 plus 9 all over 1 plus 4, because I'm getting rid of this, and this is going to be 1 minus 2. So we get for this one is going to be minus 16 over 5. And then we can do something very similar for c. c is going to be 25 over 6. Okay, so when we're done with this, we know that this is going to be equal to 1 over 30 s plus 4 minus 16 over 5 s minus 1, and then plus 25 over 6 times s minus 2. Now, I know that I'm going to have to take the Laplace inverse of both sides, so let's do that. And when I do this Laplace inverse, I'm going to rewrite these with their coefficients out. So this is going to be the Laplace inverse of I'm going to say 1 over 30 times 1 over s plus 4 minus 16 over 5 times 1 over s minus 1 plus 25 over 6 times 1 over s minus 2. Now remember that when we're done with this, this is our solution. So capital F of t, or I can say y if you'd prefer, if you want to write this as, y equals, because these things say y. Capital F of t, or y, is going to be 1 over 30. This is e to the minus 4t. Minus 16 over 5. This is e to the t, 1t, and then plus 25 over 6, e to the 2t. So if you like the videos, you want to help us grow our channel, like, subscribe, and share.